So not only can we solve systems of equations that have two variables, we can also solve systems of equations that have three variables. Now, solving systems with three variables is very similar to solving systems with two variables. The only difference is that, other than that it looks different graphically, but there's also extra steps involved. Other than that, the same rules for solutions for two variable systems still apply for three variable systems. Instead of looking across, instead of looking at an intersection across just x and y, now we also have to consider looking at solutions in terms of three dimensions, x, y, and z. Okay, so when you're whether we solve two-dimensional systems of equations or three-dimensional systems of equations, the solutions still end up being the same concept. A consistent and independent system, which has one solution, is made up of three equations whose planes intersect at one common point. Okay, so if I have three linear equations in x, y, and z, and it's a consistent and independent system, it has one solution. Both of those, the planes that represent those equations intersect at one common point, x, comma, y, comma, z, comma. Okay. So again, think of like x, y as horizontal, your horizontal axis, your vertical axis, but z is now your third-dimensional axis. Okay. A consistent and dependent system having infinitely many solutions is made up of three equations whose planes intersect at all points along a common line, either x equals, y equals, or z equals. And remember, when we talked about consistent and dependent systems, for two-dimensional, for two variables, it usually happens when one equation is a multiple of another. This is still the same case with three. It's still the same case with three different variables. If one of those three equations, if either you have, let's say I have a three variable system. If I do not have three equations, if let's say I have two, or let's say one of those three equations is a multiple of the other, that's when we have a consistent and dependent system, and then we're looking at writing our equation, our solution, in terms of one of these variables. Then we have an inconsistent system, having no solutions, is made up of three equations whose planes do not intersect at all. So all three of them do not intersect at a single point or at a line. Let me show you an illustration here. So here's an illustration where you have no solution, right? There's no one space, there's no one spot where all three of these planes intersect at the same time. You could have three parallel planes, but you could also have only two planes that intersect, but not three. And same thing here. With one solution, the planes intersect at one common point. So here's an example of an illustration where I have three planes, an x-plane, a y-plane, and a z-plane, and all three of them intersect at the same time at that one spot. Then we have an infinite number of solutions, a consistent and dependent, where they intersect, but they intersect in a line. So that you have multiple points where they intersect according to that line. Now, when we are looking at systems of equations, remember we talked about how we can solve them graphically and algebraically using substitution and or elimination. For systems with three variables, we're obviously not going to be able to graph three different planes and find their intersection, not without like in a really advanced graphing calculator. So our best option is to use substitution and elimination. Now, if you can use substitution, then you're very lucky, but most of the time you'll have to use elimination. Now, when we're using substitution and elimination, one goal to have in mind is to eliminate as many variables as possible so that substitution can be the easiest to use. For a system of equations in three variables, that means finding ways to convert the system to a form that makes it easy to substitute. Okay? And that's where we get to this definition right here. There we go. So a row, rewrite that again. Row echelon, E-C-H-E-L-O-N. A row echelon or triangular system of equations is a system in which the left side of the system forms an inverted triangle in which the leading coefficient for each equation is 1. The last equation contains only one variable, and each equation above it contains the variables from the equation immediately below it. So here's an example of a triangular system. My first row, I have x, y, z equals a number. Here I have y and z equals a number. And then my last row, I have z equals a number. Now with this example, because it's in triangular form, I can go ahead, I know what z is. Let's take that, plug it into here, figure out what y is. Take that, plug it into here, figure out what x is. Let's use that as an example. Z is negative 2. Okay, z is negative 2. So I'm going to take negative 2, plug it, substitute it in here. Y plus 4 times negative 2 equals negative 5. So that's y minus 8 equals negative 5. Oops. Sorry. Erase that here. Add 8. Y equals 3. Now I know what y and z are. I'm going to substitute that into the first one for x. To solve for x. X minus 3 minus 2 times negative 2 equals positive 5. Plus 4 equals 5. That's x plus 1 equals 5. Subtract 1. X equals 4. So so now that I have a value for x, y, and z, this is a consistent and independent solution. Or consistent and independent system with one solution, which is 4, 3, negative 2. So we write, for 3 variables, we write our answer as an ordered triple for x, y, and z. Okay. So notice how the left side of that say triangle, but really system. Notice how the left side of the system is in the shape of a triangle. The second row doesn't contain x. The third row doesn't contain x or y. Lastly, the third row has only one variable by itself, and then, of course, it fits the description of being in row echelon form. So the way that we convert systems of equations into row echelon form was given by a name inspired by a German mathematician called Friedrich Gauss. And that method is called Gaussian elimination, G-A-U-S-S-I-A-N, Gaussian elimination. That's the process by which systems of equations are converted to row echelon form. All right. So let's look at an example. So looking at this example right here, we're going to solve this equation using Gaussian elimination. Okay. I have 2x minus y plus z equals 4, x plus 3y minus z equals 11, 4x plus y minus z equals 14. All right, so remember, actually, let me go ahead and go back to OneNote so we can show you. Okay, so I'm going to use this space to write out this problem here. All right, here's my system. I have 2x minus y plus z equals 4. Then I have x plus 3y minus z equals 11. And then I have 4x plus y minus z equals 14. All right. So remember, there are 3 different ways that we can work with a system of equations. We can either change the order, we can multiply by an equation by a non-zero real number, and we can add or subtract a row to each other. We're going to end up using all 3 in this problem in some form or another. So first thing I want to do is, let's go ahead and just take these 2 equations and switch. I just kind of like to have my x's in numerical order, just because it kind of makes it look a little bit neater. So I'm going to take row 1 and I'm going to switch it with row 2. Okay. And so I get x plus 3y minus z equals 11. 2x minus y plus z equals 4. and 4x plus y minus z equals 14. Okay. Now, what am I looking to do? Well, first I want to try to eliminate as many variables as possible. I want to try to eliminate as many variables as possible so that I get it in triangular form so I can solve it. And again, there's more than one way to do it. So whichever way you do it, as long as your math is correct, it should lead you to the right answer. There's not one correct way to do it. So here, I want to keep this equation intact. I want to eliminate the x here from this equation, and I want to eliminate the x and the y from this equation right here. All right. So here's what I'm going to do. I'm going to do as much of my scratch work on this side as possible so I can keep this intact. First thing I want to do, so if I number these, 1, 2, so row 1, row 2, row 3, I want to get rid of all the x's in rows 2 and 3. The only way I can do that is to multiply this entire row by a number that's going to cancel these out. So for my first trick, so x plus 3y minus z equals 1. For my first trick, what I'm going to do is I'm going to take negative 2, multiply it into here, and I'm going to add it to this row so that I get a new second row. All right, so negative 2, row 1, and I'm going to add that to row 2. And that's going to be my new row 2. Then I'm going to take the same row 1. I'm going to multiply that by negative 4 and add it to here to get rid of that 4. Okay, so negative 4, row 1, plus row 3. And that's going to be my new row 3. All right, so those are the first two steps that I'm going to, those are the next two steps I'm going to do. The very first step was switching these two. Next step is to eliminate the x's. So here's what I got. So I'm going to first take this, multiply it by negative 2. All right, so here's what I get. So negative 2x minus 6y plus 2z equals negative 2. So remember, when you multiply an equation by a non-zero real number, you got to multiply every part by that number. So negative 2 times this, negative 2 times this, negative 2 times this, negative 2 times this. Okay? I'm going to add the second row right here. X plus 3y, I'm sorry, 2x minus y, 2x minus y plus z equals 4. So now the x's eliminate each other, and I just combine the other like terms. Okay, negative 7y plus 3z equals negative 2 plus 4 is 2. So that's my new second row. I'm going to go ahead and put that here. Negative 7y plus 3z equals 2. All right. Now I'm going to take row 1 here. I'm going to multiply that by negative 4 and add it to the third row. Okay, so x times negative 4, that's negative 4x. Okay, times negative 4, that's negative 12y. And then positive 4z, so plus 4z equals negative 4. And then I'm going to add this third row here. 4x plus y minus z equals 14. Minus z equals 14. So now x's will cancel. Negative 12, let's see, negative 12 plus 1, that's negative 11y. 4 minus 1, that's plus 3z. Negative 4 plus 14 is 10. So there's my new third row. Okay, so negative 11y plus 3z equals 10. So I'm done with row 1. I don't need row 1 anymore. Now, also, row 2 has my y and z. So I'm going to leave. So I'm going to keep this intact, but I'm still going to use it because I want to eliminate that y right there. Now, how am I going to do that? Well, I need to find a common multiple of 7 and 11. Well, the only common multiple is 77. So here's what I'm going to do. Remember, this is row 2, this is row 3. So what I'm going to do from here is I'm going to take this row, all right? I'm going to multiply that by 11. So 11 times row 2. I'm going to take negative 7. Now, why negative 7? Well, I'm multiplying this one by 11, so this term will be negative. I want this term to be positive. So that's why I'm going to multiply this by negative 7, because negative times negative is a positive. So plus negative 7 times row 3, and that's going to be my new third row. That's going to be my new third row. So let's go ahead and do that. See, this is negative 77y, okay, plus 33z, and then that's equal to 22. Plus. Now I'm going to multiply everything by negative 7 here in the third row. So that's positive 77y. So 3 times negative 7 is minus 21. And then 10 times negative 7 is negative 70. The y's will cancel. 33 minus 21 is 12. And I need to calculate 22 minus 70. Got my calculator right here. 22 minus 70, negative 48. Now obviously I can write. Go ahead and rewrite my system. X plus 3y minus z equals 1. Negative 7y plus 3z equals 2. Now, obviously, I can write 12z equals negative 48. But come on, I'm trying to figure out what z is. So let's just go ahead and divide by 12 on both sides. Z equals negative 4. Now, it's not quite in triangular form because that negative 7y right there. But here's the good news: you don't have to put it quite in the perfect triangular form. All you need is just 3 variables here, 2 variables here, 1 variable here, and from there we can use our substitution to find the solution to this equation. So I already know what z is. Let's substitute it in here to figure out what y is. So negative 7y plus 3 times negative 4 equals 2. Okay, that's negative 7y minus 12 equals 2. Add 12 to both sides. Negative 7y equals 14. Divide by negative 7. Y is negative 2. So now that I know what y and z are, let's plug it in, substitute this first equation to find the value for x. So x plus 3 times negative 2 minus negative 4 equals 1. So that's x minus 6 plus 4 equals 1. That's x minus 2 equals 1. Add 2 to both sides. X equals 3. All right, and there is my solution. Okay, there's my solution. I'm going to go ahead and write it out as an ordered triple. X, which is 3, y, which is negative 2, and z, which is negative 4. This is a consistent and independent system. Now, let's say I have equals something, y plus z equals something. Let's say that I'm solving my system of equations and I end up losing one of my equations due to it being a multiple of another. Then at that point you have yourself a system of equations that's consistent and dependent, and you'd have to end up writing one of those variables in turn. You'll have to figure out how to write out the equation of the line for that particular equation or system. Now, also keeping in mind that even something like this still applies. If you come up with something that doesn't make sense, that's no solution here. It is an inconsistent system. But if it turns out one of your equations is a multiple of another, like for example, I used x plus y plus z equals 1, y plus z equals 2, and this is negative x minus y minus z equals negative 1. If I use elimination and I combined both of these two together, I completely lose that row. And then I have infinitely many solutions. Which means that this is a consistent and dependent system. Okay, so we got to be careful when we're doing our elimination to make sure that we are 100% looking out for both of these situations as well as a normal solution.